Hello, today I will be talking about molecular descriptors with actively identified subspaces for molecular property optimization. So to begin, we cannot optimize molecules in molecular space. Instead, we need a numerical representation. If we can reversibly map to and from that space, then we can solve molecular property optimizations with derivative-free methods. Numerical representations of molecules are generally high-dimensional though and require some sort of encoding. So our proposed method, MolDAIS, uses molecular descriptors, sets of rotationally and translationally invariant calculations done on a molecular graph, coupled with active subspace identification, motivated by interpretable machine learning models that posit a relatively small number of features to actively predict the property. In this work, we use the sparse axis-aligned subspace GP prior. Putting this all together, we get molecular descriptors with actively identified subspaces, or MolDAIS. So our first case study is on experimental lipophilicity. It's a relatively small data set with 4,200 compounds and their corresponding values. Here in the lower right, we see the convergence results where MolDAIS is doing fairly well, although maybe not particularly impressive. But when we look at the distribution of final values, we see that generally MolDAIS typically does well and has the best worst case scenario. In our second case study, we consider the log P optimization benchmark. This is another lipophilicity data set consisting of 250,000 commercially available molecules. In this larger space, we start seeing increased performance by MolDAIS, really breaking away from the other optimizers. Up in the top right-hand corner, we see that all of the runs were able to find the optimal molecule in this data set with just 100 iterations. For our third case study, we consider the power conversion efficiency from the Harvard Clean Energy Project. This data set contains nearly 30,000 compounds and their corresponding CEP values. In this larger data set, we again see high performance by our proposed method MolDAIS, significantly outperforming the other methods. Similarly, looking at the distribution of final values, we see that we often find the best solution, but always have a best worst case scenario. We also extended this method to consider constraints. Shown here is the performance or convergence plots for the constraint problem. And we again see MolDAIS significantly outperforming the other methods. And looking at the distribution of final values, we see a best case scenario, while none of the methods found the optimal. And we do see a pretty good worst case scenario as well, better than some of the other methods. So in conclusion, our proposed method, MolDAIS, combines molecular descriptors with a sparse axis-aligned subspace prior that actively learns an encoding while performing Bayesian optimization. And through this method, we can efficiently identify high-performing molecules in the low data regime. Thank you for listening, and special thanks to everyone who helped make this possible.